Hello, everyone. I'm Ahmed Nademi, Assistant Professor of Electrical Engineering at California State University, San Marcos. So I'm going to present the result of the study entitled Real-Time Model Development of the IEEE Benchmark Distribution Feeder Test System for Microgrid Stability and Controls. So this was the collaborative research project across several universities, as you can see here. The outline of this presentation is the background and motivation for real-time simulation, basically to answer this question: why do we need a real-time simulation for microgrid stability analysis? The challenge for the distributed energy resources, DER's integration into the power grid, medium voltage distribution network is the interoperational dynamic interactions, interface system integration requirement, pose huge challenges for modeling and also the stability analysis. And then there are a lot of initiatives needed, or demands are quite high to study the optimal integration of the DERs to the grid, energy storage, optimal dispatching, and also the distribution load leveling. Real-time model development for IEEE microgrid benchmark test case is captured by the IEEE Power and Energy Society PES technical report TR66, which was the release in 2018, the task force on microgrid stability analysis and modeling as well. So this study addresses the gap for education and also establishing some guideline for researchers interested in this subject to validate the switching equivalent circuit for the power electronics devices, component interfacing the generation units like solar PV, battery energy storage, wind turbine, and diesel generators. And also, in addition, the industrial distribution loads such as variable speed drives, motors, capacitor banks, and also the variable loads. To study the common AC DC bus energy management in terms of the dynamic phenomena, verify the control algorithms to achieve the high fidelity and also accuracy of the result by doing the real-time simulation. And at the end, I present the real-time simulations of the operating case scenarios, and also followed by concluding remarks. The technical challenges, mainly by huge integration of the power electronics devices, is to demand the test for the real-time compatibility and proposed models for the utilities, developers, renewable energy developers, and also to implement testing of different control strategies to achieve those huge integration to the power networks in a successful manner. The contribution of the real-time simulation is basically to reduce the cost to replace the real hardware by the real-time model, and then to achieve as accurate as a result compared to the renewable energy or HDR's physical counterparts. And also it's possible to integrate the external devices like sensors, controllers, or actuators to the real-time model with no cost and risk, or at least reduced risk. So this schematic diagram shows that introduced IEEE test case for the microgrid dynamic and stability analysis. So there is an 80 kilowatt solar inverter and also a 50 kilowatt hour lithium-ion battery bank, followed by the 20 kVA inverter, and also we have a 50 kilowatt diesel generator feeding the common AC 400 volt bus, and also the common bus is supplying the two variable speed drives and also the direct online motors at the rate of 20 kilowatt. And also we have a zip load model. It is worth noting that in this study, to better analyze the dynamic phenomena, we replace the zip load model with the variable load, and also we have the capacitor banks as well. So this is the implemented or developed the IEEE feeder test in the RT-LAB software to be able to execute the real-time simulation and testing through the opal-rt platforms. So this control diagram shows the power stage, the bidirectional DC-DC converter, and its associated voltage control and also current control strategies for the battery energy storage device, which is the focus of this study. So the output of the current controller is to send the 4 duty cycle signals or switching pulses to the 4 IGBT switches comprising the power electronic component or stage of the bidirectional DC-DC component. So we use the Corvus AT6500 single battery module to model the lithium-ion battery with the power level of 44.4 volt and also the capacity of 90 amp hours. And also the voltage for the battery pack comprising the 4 single batteries is from the minimum voltage is 924 volt up to 1050 volts, and with the state of charge of 60 should be about 60%. So this graph shows the operational characteristics of the use the battery in this study. So for the control strategies, we have to control load for the energy storage batteries. As you will see, the green block voltage control and also the middle block is the current controller. So in order to compromise the current and voltage control strategy, we have considered the 4 operational modes for the bidirectional converter depending on the direction of the current and also the battery energy storage. If the battery is in the charging mode, the positive current is assumed, and vice versa. If the battery is in the discharging mode, the negative current is assumed, and then different switching pulses will be sent out to the 4 IGBT switches. And also the DC link, the intention is to be kept at the range of 880 volt to the 1050 volts, and also the upper limit should be exactly, and also when we reach to the upper limit or lower limit, the PI controller from the battery energy device controller could be activated to be able to maintain the DC link voltage for the battery energy storage device and inverter within the specified characteristics. So another control input is the state of the charge, SOE status, for regulating the output current reference. So some exemplary real-time testing of case studies is presented here. We have measured the active power for the battery energy storage device. The green curve, the red, shows the diesel generator power, 45 or 50 kilowatt power, and also the blue curve is the PV inverter in the range of 80 kilowatt power. And also we have done some tests to be able to evaluate the performance of the controller with respect to the DC voltage reference tracking for the PV inverter and also for the battery energy storage devices. As you will see, the obtained or measured curves can be able to follow exactly the reference for each PV inverter, which is the range of the 480 volt, and also the reference voltage for the battery energy storage device is 1030 volts. And also the measured typical waveform for the battery pack, including the 4 single batteries, as I presented earlier. During the charging mode, it shows is shown here, and also the state of charge here, as you will see, is almost 85%, and also the output DC voltage is exactly for 4.4 volt would be around 177 volts, and also the output current during the charging mode, it should be plus 110 amps, as you will see in this graph. And also we have done some transient phenomena studies when, for example, the diesel generator genset is disconnected at a time instant of 4 minutes, and also while the variable speed drive torque reference has been increased by 50% from 11 Newton meter to 16.5 Newton meters at the time instant of 7 minutes, as you will see here. And also the measured torque response is perfectly follows the load reference, torque load reference, fulfilling the optional requirements. And also the final transient test scenario is applied, for example, when the diesel generator was under the dynamic operating conditions, disconnected at time instant of 4, and as you will see, and also when the VST motor torque has been increased by 50% at the t equal to 7 minutes. here, and then the mechanical speed and also the stator terminal voltage maintains within the specified for the diesel generator during this dynamic transients. So this work developed the real-time model for the microgrid using the use case introduced in the IEEE PES-TR66 technical report to study the integration challenges of the DERs and also the interaction between the dynamic load like variable speed drives and the motors, capacitor banks with the interfacing with the common AC or DC bus, and also to analyze or to validate the control algorithms and load characteristics and their effects, interestingly, on the microgrid stability. So for our future work, we will explore the further real-time testings for the other DRs like a PV inverter and also the wind turbine and its associated control strategies. Thank you for your listening, and I would be more than happy to take your questions.